Everyone, in this video lesson, we're going to do some problems involving generalized projectile motion, where instead of being launched horizontally and the initial vertical speed is 0, we'll do some problems where we maybe launch a projectile in the air, so above the horizontal or even below. So let's get started. And as a bit of a warning, this video may be a bit longer than kind of the half an hour we're used to doing, just getting a few examples in there. So if you definitely need to just take a break in the middle, you can luckily do that at home. Just pause me and come back whenever you're ready. Or just break this up into 2 little lessons, whatever you prefer. So what have we done so far? Right now we've considered projectiles where they've been launched horizontally and the vertical speed v1y was 0. So the launch angle was 0 degrees. So in general, obviously, this doesn't need to be 0. In this case, to analyze our problems, we have to take the muzzle velocity. So that's like the muzzle speed combined with its initial launch angle. And we have to calculate our Vx and V1y at the start. So in our previous example, and maybe in the practice questions you did, the Vx was given to you and V1y was 0. Well, now we have to calculate those two things before we do a problem. So we're going to be mainly just doing examples today. So here's our first situation. So we have a cat being launched out of a cannon. And this cannon is located on top of a tower, 120 meters above the ground. We're going to launch the cat from a 30-degree angle above the horizontal and below. So not very good at drawing towers, but let's say there's a tower. And we have our cannon and our cat is launched out of the cannon. And so we have 2 cases here. For part A, we're going to be launching the cat at 30 degrees above the horizontal. And for part B, we're going to launch it below. Now, hopefully, it's pretty obvious, in which case the cat is going to travel farther. We're expecting in part A to get a horizontal distance traveled to be a lot bigger than we get in part B. So this question is just to get you guys used to calculating V1y and Vx initially. And in our last lesson, I used down as positive for our projectiles because they were landing down. In this particular problem, I'm just going to mix it up, and I'm going to choose up to be positive. So a couple things to keep in mind for each of these parts. Our acceleration will be negative 9.8 meters per second squared. In each of these cases, the cat's going to be going from the top of the tower to the ground, and that is 120 meters high. So our displacement vertically in each of these problems will be negative 120 meters. For parts A and B, our Vx is going to be equal to, so V naught times the cosine of the angle. So that's 30 meters per second times the cosine of 30 degrees. And so that's going to equal, if we just do 30 times cos 30, put 20, basically 26 meters per second. And again, that's for A and B. And for, let's actually just leave it as that for the initial setup. And let's go on to, so that's going to be the same for each problem. So let's go on to part A. How far will our cat travel? We launch it at 30 degrees above the horizontal. So just to recap, we have picked up as positive. We have, therefore, our acceleration, negative 9.8. Our delta dy, negative 120 meters. Vx, we got 26 meters per second. And that's what we know so far. Our V1y, in this case, if we think about it, we're launching above the horizontal. So our cat initially will be moving upwards. So our v1y should be positive. It'll be the positive of our v naught times sine theta. So it's going to be 30 times the sine of 30, which is 15 meters per second, because sine 30 is 0.5. Yes, it is. And it's positive, again, because it's going up. So in part B, when we do part B, we'll have this exact same setup, except v1y we know will be going down. So 15 is that gives the size, but we'll have to take care of the sign. It goes down. And in this question, we are asked to find delta dx. So this is actually a lot like the cannonball question we did in our last lesson, where the connecting factor is going to be the time. So even though the question doesn't say find the time, it will be helpful for us to do that. So let's get started. Let's find that first. So we have delta dy, a, and v1y. So it makes sense to use delta dy equals v1 delta t plus 1/2 a delta t squared. So unlike our horizontal, our v1y is not 0. So we will have a quadratic equation to solve here. So we get negative 120 equals 15 delta t. And then we'll have minus 1/2 times 9.8 minus 4.9 delta t squared. And in this case, I'll use the quadratic formula, 4.9 delta t squared, moving things to the left, minus 15 delta t minus 120 equals 0. So we have to solve this quadratic equation. So if you want to pause the video and do that and come back and check an answer, that's fine. Or just want to follow along with me, whatever you want. So 15 plus or minus, so b squared, negative 15 squared, minus 4.9, minus 4 times 4.9 times negative 120. And all this will be divided by 9.8. So I'm going to do this in one step just to save some room on my board. We all have lots of practice with the quadratic formula. Just going to have to assume you guys are somewhat proficient at it. So 15 squared plus 4 times 4.9 times 120. Square root that. Add 15 divided by 9.8. So I got about 6.7 seconds. That was using addition. Using subtraction, we will get a second value for this. So 225 plus 4 times 4.9 times 120. Second root equals plus 15 divided by 9.8. All right, and we got for a second time, negative 3.6 seconds. So we can ask ourselves, do both of these values make sense physically, or does just one? And it's just one, 6.7 seconds. The significance of that other value is if we're doing part A here. We just found that we're going to land just, at 6.7 seconds. But if you took this parabolic path backwards, say in time, the time it would take to get to the ground on this side would be 3.6 seconds. But obviously, time is moving forward from 0. So we're going to be choosing, obviously, the 6.7 seconds one. And now we are ready to go because we have the time and we have the horizontal speed. The horizontal distance is just speed times time, 26 meters per second for 6.7 seconds. And we have how far our cat will travel, 26 times 6.7, about 174 meters. And we've solved part A. That was an example of a kinematics problem where we we're solving for delta t. And remember, we had two ways to do that. One is to set up a quadratic equation and solve. For part B, maybe let's do it our second way. But for part B, what changes? So the acceleration is still negative 9.8 meters per second squared. Our delta dy is still negative 120 meters per second. Our Vx, unchanged, 26 meters per second. In this case, our V1y. So I want to just talk about a couple things. So we know we're going to get V1y by doing the muzzle speed 30 times the sine of the angle of the launch angle. And this time it's 30 degrees below horizontal. So you can do 30 sine 30. And in this case, we just have to remember, we know up is positive. So we know we have to add on that negative. And so we'll get negative 15 meters per second. Alternatively, and if you want to do this, you can. If you took the grade 11 math course, you know that you can actually have negative angles too. And that sine, cosine, and tan, there's like certain rules for whether the sine or cosine or tangent of a negative angle is positive or negative. If you view the angle instead of being 30 degrees below the horizontal, another way to say that is to say that the angle is negative 30. So if you do the sine of negative 30, you're going to find that gives you negative 0.5, and you get negative 15 meters per second. So my advice, because a lot of the times I teach this course, there's many grade 10s who actually haven't taken the grade 11 functions class. My advice is just use V naught sine phi, the launch angle, and then just make sure you have a care of what the sine should be. That'd be my advice to you. All right, so I'm going to show you guys an alternate method. So we do need to find delta t so that we can find the horizontal range like last time. And you could totally just set up this problem just like the last example we did, do the exact same method. Or what you could do is you could find V2y. It's a bit of a way to avoid using the quadratic formula. How can you do that? Well, I'll show you. So if we use this kinematics equation, V2y equals V1y plus a delta t, we can find the, we can't use that, excuse me. Because we have delta d and not delta t. So we can use this kinematics equation, V2y squared equals V1y squared plus 2 times a times delta dy. Because we know these three things, right? So V2y squared equals, so negative 15 squared plus 2 times negative 9.8 times negative 120. So V2y squared, we can work that out. So 15 squared plus 2 times 9.8 times 120. So we get, for V2y squared, 2,577. Now we have to be careful here. This is V2y squared. There are two numbers that when you square it, give you 2,577. One of them is the positive root of 2,577, and one is the negative root. So you have to be careful using this method that you choose the correct sign. We know we chose up to be positive, and we know when the cat strikes the ground, its vertical direction, it'll be moving in the downward direction negative. So we here want to take the negative. If you were unsure, then you could use the previous method, quadratic formula, and that won't fail you. But here, we're going to take the negative, and it's about negative 50.8 meters per second. And now we can find the time by using this kinematics equation. Because now that we have V2y, that should be a plus, we have V1y, and we have a, we can find delta t by doing V2y minus V1y divided by a. So you could argue, is this a bit more work? Is it a bit less work? I guess it just depends on personal preference. But with this way, you do have to be careful with your signs, especially finding V2y with that equation over negative 9.8. So all these negatives will give us a positive time. So that's good. 9.8 minus 15 divided by negative 9.8. I got 6.7 seconds. Okay, just going to double check because that does seem weird that we got 6.7 seconds. It should take less time to reach the ground. So I'm just going to double check my work from the previous question. So we had V1y is 15, 15 delta t, that over, that's positive, negative, negative, negative b. Everything is looking pretty good. Did we do everything right for this part of the question? V1y is negative 15. Oh, I see what the problem was. Yeah. So if you're kind of screaming at your screen that I missed something, I have figured it out. So V1y is negative 15. So I should be subtracting negative 15. Excuse me. Yeah, normally teaching summer school like this, I've got a class full of students that would, half of them at least are bound to find mistakes like that, but not so teaching online. So it's got to be careful. And if you guys ever see me make a mistake during a lesson, hey, it happens. Let me know, and I can fix it up, or at least post like a correction video or something. So this makes more sense. Here we have, I got about 3.7 seconds. Hit the ground. Now, if you had used a quadratic formula, this would be one of the times that would have been spit out. So, finishing it up, we can now find delta dx. Dx delta t is 26 meters per second, but this time it's only in the air for 3.7 seconds. So we'll get a much smaller horizontal distance covered. 7 times 26, about 96 meters. All right, so again, the bridge between the two directions, horizontal and vertical, is often the time. So here we had to find the time to get the horizontal range. But to find the time, we had two methods. You could use the quadratic formula by using the displacement curve equation, like in the first method, or you could find V2y and find delta t that way, but just be careful with signs. All right, so let's do a different type of problem, one where we calculate muzzle velocity. So if you recall Kawhi's famous shot over Joel Embiid, we're almost at as I shoot this video, we're almost at the year anniversary. We're a bit past that actually of the Raptors championship. These figures I just estimated based on a typical NBA player's height, and how high the bat net is above the ground, et cetera, et cetera. So let's say that Kawhi, excuse me, taking his jump shot, he released the ball when the ball was 2.9 meters in the air, and the ball traveled 5.8 meters horizontally to get to the basket, and the standard NBA net is 3 meters above the ground. And if we know that the ball was in the air, it had a hang time of 1.5 seconds before hitting the rim, we should be able to work backward and find the muzzle speed and the angle with which Kawhi launched his shot, and hence get the muzzle velocity. So what are the things we're given in this question? So obviously we have the time of flight, 1.5 seconds. What we don't know is, or what we do know is delta dx. We know that the ball traveled 5.8 meters horizontally while it was in the air. And we do know delta dy as well. Now we have to be careful here. Delta dy, the final height of the basket, was 3 meters. Actually, and before I choose, give that value, we should choose a direction to be positive. I might choose up to be positive here. So if Kawhi released his shot at 2.9 meters, and the ball hit the basket rim at 3 meters, that means the displacement, the final position was 3 meters above the ground. The initial was 2.9, and that means this vertical displacement is 0.1 meters. So notice that didn't appear anywhere in the question. The change in height of the ball was 0.1 meters. It just went up in the air and came back down to have that displacement. So hopefully that made sense to you. And I think we have used everything. So what do we need? Well, we actually know, obviously, acceleration to gravity is negative 9.8 meters per second squared because we chose up to be positive. To get the muzzle velocity, we need to know how far or how fast is the ball traveling horizontally. And we have to find V1y. If we can know those two things, we can put things together. Now, one of those is actually very easy to find. Vx is easy to find because we know that the ball traveled 5.8 meters in 1.5 seconds. And so our Vx is just doing that division, 5.8 divided by 1.5. I'm going to call that 3.9 meters per second. Okay, so we got Vx. That wasn't too bad. Can we find V1y quickly and efficiently? And we can. If we look at the displacement curve equation, delta dy equals V1y delta t plus 1/2 a delta t squared. We know a, delta dy, and delta t. So we can actually find V1y. Now, whether you want to solve this equation for V1y first, that could be a bit messy, or if you just want to plug in right away. For me, I don't see the big deal with this one, with just plugging in right away. Normally, I do like to isolate, but let's just plug in. Delta t was 1.5. So we have 1.5 times V1y. And then we have, it'll be plus 1/2 times negative 9.8 times 1.5 squared. So I'll just do things in a couple steps here. So that's 1.5 V1y. That's going to give me, so we'll have 4.9 times 1.5 squared. So we'll have minus 11.025. So I'll take 0.1, I'll add my 11.025. And if I divide by 1.5, that'll isolate V1y for me. So V1y is, you should do it too. I got about 7.4 meters per second. All right, so knowing those, we are now ready to find the muzzle speed and angle. So I'm actually just going to flip to a second screen for that. So Kawhi is shooting over Joel Embiid, kind of like this. We're looking for, we'll just call it V. And the things we have found already, we have already found Vx and Vy, V1y. Vx was 3.9 meters per second. V1y, 7.4 meters per second. So let's find that launch angle. Let's find that launch speed. You guys are hopefully old hats at this now. So if you want to pause the video, just do it yourself or just, fast forward. Will not be offended for sure. Use Pythagorean theorem for that. And theta, the launch angle, inverse tan of 7.4 over 3.9. By 9 squared plus 7.4 squared and root it. Put 8.4 meters per second, and the launch angle 7.4 divided by 3.9. Shift tan. So a pretty steep launch angle to get it over Joel's hand, about 62. Let's just call it 62 degrees. And we've got it. So the muzzle speed, muzzle velocity, I should say, was 8.4 meters per second, and it was 62 degrees above the horizontal. So just a different type of question, Really nothing crazy different than the first one we did. Just solving for different variables. We're going to do one more example together, where we look at a ground-to-ground scenario where the projectile is launched from a certain height, and it comes back to that height. Because in those cases, we have some really nice symmetry, and there's actually some useful equations that we can use to predict how far something travels if it's launched from ground to ground, and how high it would reach above the ground as well. So here we're going to look at a golfer striking a ball. So most people should be familiar with golf, hopefully at least, but if you're not, that's okay. So this golfer is going to be striking a golf ball from the ground, and it's going to go up in the air, and it's going to come back down, and it's going to hit the ball some distance down the golf course, but at the same height. So in this question, we're going to call that delta x, the horizontal range, because we're actually going to derive a formula for the range in these type of problems, and then we'll use that formula to find our answer. What we're also going to be interested in finding is the maximum height that the golf ball reaches, and we're going to call that delta y max, the maximum displacement above the ground. We may also, while we're doing this, find an expression for the flight time, how long this projectile would be in the air, and we'll call that delta t. So this is kind of where we're going at. Now, with a ground-to-ground scenario, there's a few different things that are important to talk about. One is when we're finding delta y max, if you think about at the top of the projectile's arc, the motion is purely horizontal. And so at the top of a projectile's arc, v2y is 0 meters per second. The motion is purely horizontal. So keep that in mind. We are going to use that for finding delta y max. And the second piece of info we'll use is this. Now, this isn't a proof, but we could prove it. But hopefully it just makes sense based on the symmetry. So when we hit the golf ball, it's going to have some initial component of speed, vertical speed, v1y. When it lands, because of the symmetry of the problem, it's going to have the exact same speed. It'll just be in the opposite direction as v1y. v2y and v1y will have the same speed. They'll just be pointing in opposite directions. So we're going to make use of that in our first problem here. So let's do it. Let's talk about the range. We're going to get an expression for we're going to derive an expression for the horizontal range. So if we're doing part A here. So the key, and I'm going to choose up to be positive as we derive these. And I'm going to start with this kinematics equation. V2y equals v1y plus a delta t. I'm actually going to get an expression for delta t. So if I solve that equation, I get delta t equals v2y minus v1y divided by a. Now in our problem, remember, v2y is negative v1y. We discussed that on the previous slide because of the symmetry of the problem. And because I chose up to be positive, I'm going to replace a with negative g. Negative because my acceleration is down, and I chose up to be positive, and g being 9.8 meters per second squared. But I'm going to leave it as g so that we can use these formulas for wherever we are on Earth, or we can use these formulas for whether we're finding a projectile motion on some other planet where g is different. Let's continue. So we get negative 2 v1y over negative g. So there's two things here. The negatives will divide out. And I can replace v1y. I'm going to replace it with the following. Remember, v1y is the muzzle speed times the sine of the launch angle. So I'm replacing v1y with v0 sine theta. over g. And what this gives you, this is an expression for flight time. So for any projectile, if you know g, and you know, well, if it's on the Earth's surface, you know g. But so if you know a projectile's speed and launch angle, you can calculate its flight time using that formula. And you're just free to use that. But remember, this only works for ground-to-ground problems. Now that we've done that, we can find the horizontal range, because the horizontal range is the horizontal speed times the time that it's in the air for. Horizontal speed is v naught times cos theta. We just found an expression for delta t. It was this, 2 times v naught times sine theta all over g. Now, if we put that together, we get v naught squared times 2 sine theta cos theta divided by g. And this totally works, but there is an easier way to write this. For those of you who have taken some high-level math courses, you have actually seen that this expression 2 sine theta cos theta is actually an identity. And in Appendix A of the Nelson textbook, they have some identities you may find useful. But for those of you who haven't taken those math courses, you can just take my word for it. That 2 times the sine of an angle times the cosine of the angle is actually equal to the sine of 2 times that angle. So if my launch angle is 30 degrees, I would do the sine of 60 degrees in this calculation. You just double the angle. And that's an expression for the range. So now we can actually use that for our problem. So what's the range of this projectile? Well, the ball was struck with a speed of it left the golf club with a velocity of 42 meters per second squared. The launch angle is 32 degrees above the horizontal. So we're going to do the sine of 64 and divide by g, which we'll assume is 9.8. So these ground-to-ground formulas are pretty cool, and they can be very helpful. And my expectation is that for many of you, you didn't really derive these equations last year. You analyzed projectile motion kind of along with your kinematic stuff. So I got 162 meters approximately. So this may be new to you. And as you do problems and you realize, hey, this problem is a ground-to-ground problem, you can feel free to make use of these formulas. Just don't get trapped by trying to apply this formula to a problem where it's not ground-to-ground, where you may be landing on top of something or landing below. These only work with ground-to-ground. So yeah, that's the horizontal range. So that's pretty cool. So we have now expressions for the flight time and horizontal range. Of course, taking this course online, you don't really need to memorize any formulas. They're there for you. Let's do part B. Maximum height. So for part B, we're going to make use of the fact that at the maximum height, that v2y is equal to 0. So I'm actually going to start with this. v2y squared equals v1y squared plus 2a delta d. And I might actually replace, that's the kinematics equation we're using. In this case, to find the delta d we're finding is that maximum vertical displacement that I'll call delta y max. Right. If you recall, at the top of a projectile's arc, v2y equals 0. So we can actually just scrap that term, make that 0. And we get 0 equals v1y squared. Remember, v1y is v naught times sine theta. So v1y squared would be v naught squared sine squared theta. Now, most of you guys should be aware of this, but if not, sine squared theta is just a nicer notation, a nicer way of saying sine theta squared. So that's different than sine of 2 theta. This is, when you have this little superscript 2, this means you do sine theta and you square it. And we know that A, in this case, is plus 2. The acceleration is negative g, delta y max. So if I move that second term to the left, I get 2g times delta y max equals v naught squared sine squared theta. Then I can get my expression for delta y max pretty easily. I just take v naught squared sine squared theta and divide it by 2 times acceleration to gravity. So it's pretty cool. This gives you an expression for the maximum height of projectile. Now, this particular expression will work even if it's not a ground-to-ground scenario, because what this formula gives you, you launch a projectile, and it gives you that maximum height. It doesn't matter whether you come back down there, or whether you come back down to the ground, or whether you come back to the ground further. So this can be helpful for a variety of problems. So let's actually do it for our problem. Having derived that formula, the golf ball velocity, 42 squared. And here we're doing the sine of 32 degrees, but we're going to square that, divided by 2 times 9.8. So I wrote it this way as sine 32 all squared, just to help out those of us who maybe hadn't taken that higher level math course and might not be as comfortable with the notation. Again, sine squared theta like this just means do sine 32 and square what you get. So 42 sine 32 squared divided by 2 divided by 9.8. So you should do this too. And we get about 25.3 meters. Is the maximum height. So that's the one last kind of problem I wanted to share with you guys. And my expectation is that this ground-to-ground problem is new for most of you. So this kind of concludes our talk, our what we're going to do with projectile motion. Hopefully for many of you guys, it was a lot of review. But for some of you guys, there might have been a lot of new stuff in there. And so, you know, I wouldn't consider what we just did all review. You know, there's a lot of parallels between what we just did and like 2D motion. Yeah, I guess what I'm trying to say is, you know, hopefully you're okay with what we did. Hopefully you weren't overwhelmed with a lot of new stuff. You got to see a bit of that last year. But if you do need a little bit of help with this because you didn't do it so much with maybe a term that ended abruptly due to COVID-19, I'd be happy to help you out. I have posted some practice for you guys. After you do some practice, I have a bit of an assessment on projectile motion as well. We're going to talk about dynamics in 2 dimensions, and we're going to talk about extend our knowledge of motion in 2 dimensions to do some acceleration problems. You know, we just did projectile motion, which is motion 2 dimensions, but that was where the acceleration was like straight down. What if the acceleration itself has some kind of like diagonal component? And we'll also talk about relative motion. So that should be fun. Hope you guys stay well, and we'll see you soon.